To describe the quantitative relationships that we will study throughout this course, we will need to develop an efficient mathematical language. To address this need, this slide deck will introduce variables and functions. We divide this slide deck into 5 videos. In this first video, we illustrate how verbose discussions can be made more concise with the assistance of variables. In the second, third, and fourth videos, we develop a conceptual understanding of functions. In the second video, we introduce the concept of a function. In the third video, we describe the composition of functions. And in the fourth video, we present the concept of the inverse of a function. In the fifth video, we use the concept of the inverse of a function to motivate developing the square root function, and we introduce the definition of the imaginary root. We begin by illustrating how communication can be verbose and repetitive when we do not use variables. Suppose a teacher wishes to help students to become acquainted with what it means for the duration of travel to increase in proportion to the distance traveled. If students request that the lesson be taught using only concrete numbers, then the teacher is forced to present a variety of examples, such as 20 meters divided by 10 meters per second equals 2 seconds, 50 meters divided by 10 meters per second equals 5 seconds, and 70 meters divided by 10 meters per second equals 7 seconds. It is tiresome and redundant to illustrate this relationship by repeatedly calculating particular examples of duration, corresponding to particular examples of distance, divided by particular examples of speed. The following discussion shows how we can use variables to more compactly represent the relationship between travel duration and distance in this example. Let t be a specific and particular value drawn arbitrarily from non-negative numbers representing the number of seconds of travel. Let x be a specific and particular value drawn arbitrarily from the non-negative numbers representing the distance traveled in meters. And let v be a specific and particular value drawn arbitrarily from positive numbers representing speed in meters per second. In this way, we collapse a multitude of examples into a single expression. When we place t, x, and v next to highlighted regions of number lines, and then write down the equation t equals x divided by v, we do not mean that the entire yellow highlighted region of the number line somehow is the entire orange highlighted region divided by the entire blue highlighted region. In this slide deck, we have not yet given meaning to the idea of dividing two number line regions. Instead, when we say that t equals x divided by v, we mean that t is an arbitrary yet specific and particular example of a duration measured in seconds whose number value is chosen from this domain highlighted in yellow. That x is an arbitrary yet specific and particular example of a distance measured in meters whose number value is chosen from this domain highlighted in orange. That v is an arbitrary yet specific and particular example of a speed measured in meters per second whose number value is chosen from this domain highlighted in blue, and finally that we are specifically describing those various collections of 3 numbers whose particular x, particular v, and particular t values satisfy the condition that t equals x divided by v. While it might seem obvious to think of t, x, and v as particular values, failing to emphasize this understanding now is a shortcut that leads to catastrophe during calculus. Now that we have shown how a simple discussion of a relationship between travel duration and travel distance can be described both using a list of concrete examples and using compact notation involving variables, it is evident that merely glancing at an equation is only the tip of the iceberg when it comes to grasping a quantitative relationship. Equations are often accompanied by physical or visual pictures. Fine print defining and limiting the context of an expression lurks beneath the surface. When a reader deems an equation in a physics or mathematics textbook sufficiently important to require memorization, the reader should also have, at the very least, a vague sense of an argument that gives the equation meaning, if not also facility in immediately regenerating a complete derivation. In this video, we have illustrated that variables can help us to concisely express relationships between collections of numbers that can be tiresome to describe using only enumerated specific examples. In the next video, we will describe a category of relationships called functions. One of the most important tools we have for illustrating theoretical models is the ability to plot functions.